Kinetic theory. This is thermal physics video number 3 about kinetic theory. So far we've looked at the behavior of gases. Kinetic theory is a model. It's a kind of a mathematical model, and it helps us to understand the behavior of gases. And basically this model is, if you pardon my phrase, it's a load of balls bouncing around inside a box. It says that an ideal gas is made up of a very large number of elastic spheres moving randomly. Lots of little balls bouncing around inside a box. Now, there is some evidence that gases are actually made up of tiny little particles bouncing around, and I'll leave it to you to look up Brownian motion. And there are some very nice videos of Brownian motion on YouTube. For example, if you look at smoke particles jiggling around as air molecules bang into them. So we're saying that we can explain the behavior of gases and what causes pressure then, and pressure is caused by all of these particles banging into the walls of their container. Now, this is a very, very common question that you must learn this answer to. How does a gas exert a pressure on the walls of its container? The particles in the gas collide with the walls. Their momentum changes in each collision. They exert a force on the walls. From Newton's second law, F is delta mv over T, and then pressure is force over area. That is such a common kind of 4-5 mark question. Okay, so lots of little balls bouncing against the walls. Remember, there's lots and lots and lots of them. So all these spiky little force blips will average out, and you'll get an average force, and then pressure is force divided by area. Now, using this model of a gas, using kinetic theory, we can actually derive equations which work with real gases. That kind of suggests that our model is pretty accurate. However, to do this, we have to make some assumptions. And I've written down 4 assumptions here, and I suggest you learn them. It is a common question to be asked. What assumptions do we make in kinetic theory? Well, the gas is made up of a very large number of particles moving randomly. The particles are elastic spheres. That means in each collision, kinetic energy is conserved. We ignore the interactions between the particles. Later on, we'll actually consider what happens between the particles, but for the moment, it doesn't affect our derivation. We ignore the interactions between the particles, and also the actual time for the collisions we ignore because it's negligible compared with the time between collisions. Using kinetic theory, we can derive this equation. I'm not going to, I'm sticking to stuff we really need to know. You'd be very unlikely to have to derive that. You might have to derive bits of it, but basically here it is. PV is a third nmc squared bar. So what's all this then? Well, P is the pressure of the gas in Pascal, V is volume in meters cubed, N, big N, is the number of particles, little m is the mass of a particle, so Nm is the mass of the gas in kilograms. And that leaves c squared bar. Now, what is c squared bar? Well, if you imagine there's lots and lots of particles, and they've all got different velocities, c1, c2, c3, c4, up to cn. Now, if we square all of those velocities and work out the average, that is c squared bar. C squared bar on its own isn't particularly interesting. What is interesting is if we take the square root of c squared bar, we get what we call the RMS speed. RMS is root mean square. It's the root of the mean of the squares, the RMS speed. And you can think of that as the average speed of the gas particles. Now, Here's a little sum you can do. 1 meter cubed of air has a mass of 1.2 kilograms because the density of air is 1.2 kilograms per meter cubed at a pressure of 1 times 10 to the 5 Pascal, which is about 1 atmosphere. Calculate the RMS speed of the particles. So if we put those values in the equation and get the RMS speed, we get 500 meters per second. The first time you ever worked that out, that should be quite surprising. The air molecules around you, their average speed is about 500 meters per second. They are traveling very, very fast. Saying that, if you think about the speed of sound and what sound is, perhaps it's not that surprising. Now, for 1 mole of an ideal gas, then big N is Avogadro's, 6.02 times 10 to the 23 Na. So we've got PV is a third Na mc squared bar. Earlier on, we had PV equals RT. Now, looking at those two equations, you should have an irresistible urge to put them equal to each other. And if you put them equal to each other, now simplify it a little bit by defining a new constant. And this new constant, I'm going to call it K, and it is the gas constant divided by Avogadro's constant, and it's called Boltzmann's constant. About 1.4 times 10 to the minus 23 joules per mole per Kelvin, Boltzmann's constant, K equals R over Na. So put those two equal to each other, get rid of Avogadro's and the gas constant, and you get a very interesting equation. You get a half mc squared bar equals 3 over 2 kT. Now, what's so special about that equation? Well, on the left-hand side, we have the average kinetic energy, a half mc squared bar, the average kinetic energy. On the right-hand side, we have equals a constant times temperature. So this tells us that the average kinetic energy of the particles in a gas is proportional to its temperature, its Kelvin temperature. This is very interesting because it gives us an objective scientific definition of temperature. You know, what is temperature? Well, temperature isn't how hot or cold you think something is. My idea of hot and cold may be very different to yours. What temperature is, it's a measure of the average kinetic energy of the particles. That's what temperature is, scientifically anyway. For an ideal gas, the average energy of the particles is 3 over 2 kT. There's a very, very useful approximation which you may be required to use. The average energy of the particles in any system, whether it's a solid, a liquid or a gas, at any temperature, low temperatures, high temperatures, is about kT. I'm not saying it's exactly kT, it's about kT. For example, liquid nitrogen at 77 Kelvin, the human body at 310 Kelvin, a Bunsen flame at 1770 Kelvin, the core of the sun at 15 million Kelvin. Perhaps you'd like to use kT, work out the average energy of the particles in these systems. And there it is, in joules. You can always, might be more useful to change that to electron volts.